TCP and IP. All right. Now, TCP. Yeah. Well, we'll come back to that. Let's just get into this wonderfulness. All right. So first thing we have is our NICs. Our NIC is a network interface card. All right. So we have a few different options going on in this wonderful world. So come on, give me my pen. So up here at the top, we have our kind of an Ethernet port. Now, most of the time, your Ethernet ports are going to be built right into your PC. All right, if you have a newer, probably ages at this point, but almost all desktop computers are going to have the Ethernet port built right into them. Laptops, that's a different game. All right, that is not something that you can actually rely on always being there. All right, so that may be something that you might have to actually add. But anyway, desktop-wise, we have our Ethernet controller over here. This one does claim that it is a gigabit network. All right, so that is something to think about, whether you want gigabit or 10 gig or 100 meg, whatever it is. And as you can see here, this one connects via a PCI port, PCI connection. All right, and those are built right into the motherboard. And there are different size PCI connectors. We are actually at PCIe is mostly what we are using nowadays for connectors internally on the motherboard, especially for high speed. I forget what it was, 10 gig? I think it's 10 gigabit. No, it's 1 gig. 1 gig per lane, I think. And you can have like 4x, 16x. You can get stupid amounts of transmission speeds over this PCIe connector anymore. And this one's running gigabit, so that's not really too much of an issue in the long run. We also, on the wired side, we have over here on the left, we have our USB style Ethernet controller. And as you can tell, or hopefully you can tell, you see the little blue inside that USB port. Anyone know what that tells you? Audio, no chat. Okay. That's telling us that it's USB 3. All right, USB 3. All right. So inside that, it has the USB 3 connections. You can still plug that into a USB 2 port. It will still function. The transfer speeds are just going to be lower. So even if this is a gigabit network connection and you only have it plugged into USB 2, you're not going to be able to actually transmit things at that full gigabit speed. You don't have enough data bandwidth on USB 2 to be able to do that. So that is something that you need to keep into mind when you're dealing with high-speed networking. Other wired capabilities at the bottom here, we actually have one of those fiber connections that we were talking about a few classes ago. So pure fiber wire, using fiber optics and glass to transmit our network signals instead of over copper. And again, this one you can see if you look real close, it's a PCIe Express interface as well. And if you notice, there is a slight difference here in the widths. All right, so this bottom one is only like a really little one. It's only maybe like an inch long, where this one up here is probably like 3 or 4 inches. That is telling you the different type of PCI interface. So this would be probably a PCIe 1X. This one might be a 16X or 8X or something along those lines. So and that is how many PCI lanes your device is going to use. So that is something that you do need to take into account. And again, with this fiber connection here, it's a question of how fast can we transfer it. All right. Now, the thing that I couldn't come up with the other day was this little plug right here. All right. That thing, it's called a transceiver, all right, actually plugs into that square. So this end would go whoop, right into that spot right there. And then our fiber would come out the ends right here. All right. So this is the actual device that takes that electrical signal from what I'm going to call copper, just to make it easy, converts it to fiber optic. So that actually has a little laser diodes and things like that inside of it that are doing all of the hard work. So the nice thing is if this one of these goes bad, you can just pull it out, put a new one in. You don't have to replace the whole PCI card or whatever the case is. So those are often two different devices. So that is one thing that you do need to think about. When it comes to wireless technology, our main option would be this card right here. Again, this is a PCI based one, we can tell by looking right there. Is your standard Wi-Fi signal. All right, so 802.11 I believe is the protocol, or the can't think of the name off the top of my head, the specifications for that. This one, as you can see, does have 2 different antennas sticking off the back of it, which is not uncommon anymore. we're actually starting to see wireless cards that have BCI slots like this that might have 3 or 4 different antennas on them. So that is something that you do want to keep in the back of your mind as you are, dealing with wireless and things like that. However, another option might be cellular. All right. You could go have a cellular connection, and my laptop that I'm using actually does have a place for a SIM card in it. So if I wanted to, I could throw my SIM card in there, and I'd have connection to whatever wireless network that my cellular provider was providing. So I'd have a good LTE connection. I just realized that you guys can't see the PCI slot there. Anyway, the PCI slot on that fiber one looks just like the one on the Wi-Fi card over there. So just something to be aware of. But yeah, so you can have a cellular card. We can have a traditional wireless. You might have a Bluetooth card. All of these could also be over USB. So there is definitely a little bit of a give and take going on there when it all comes down to this. PCI, USB. I think I would have put these speeds in my my slides, but I forgot to. So let's do a quick little Google. Oh. So the different speeds that we are looking at here. All right. USB 3.0 is 5 gigabits per second. USB 3.1 is actually 10. All right. Where PCI 3, yeah, I was right, is 1 gigabit per lane. All right. So that if you when you're looking at your wireless, not wireless cards, when you're looking at PCIe interfaces, how many you have different options there in the long run. You said if you have a 1x, a 4x, an 8x, and a 16x slot. Button. Yeah, that button. All right. So there you can see some of the different options. So this would use 1 lane, this uses 4 lanes, that uses 8, and that uses 16. All right. So you can have up to 16 gigabits per second on this large one. Only 1 gigabit per second there, 4 gigs per second there, 8, etc. So you can get a lot of different data bandwidth. And then if you go to Gen 4 for PCIe, it actually basically doubles to 2 gigabits. I think it's gigabytes per second, not bits. So extremely different. A lot higher speed is really what it comes down to. So that's just something to kind of be aware of in the long run. So, what do I want? All right. Anyway, let's get back into this. So there is a huge benefit to go that PCIe over USB 3. So USB 3.0 only goes to 5 gig. But I mean, that's still plenty of transmit speed for a lot of different devices. So keep that in the back of your mind. All right. Next, we lead on to MAC. All right, and MAC stands for Media Access Control. All right. This is actually kind of built right into your all of your devices is really what it comes down to. This is linked to the hardware of your NIC, your network interface card. All right. So a wireless adapter has one. My other wireless adapter has one. So as you can see here in this picture, which this is not my computer, but you can see that there are 2 different MAC addresses here. Notice they both do start with almost exactly the same information. Actually, they do start with the same information. All right. So very close. The only difference is actually this last number right there, 21 and 22. So that is something that you need to think about, or not think about, but be aware of. Traditionally, this MAC address is not something you're going to change. All right. It's hard coded into the firmware or whatever of your device, and it's never going to actually change. Now that is actually starting to become a little different, and this is for security purposes that's changing. And the reason I say that is because Android now, make my picture a little bigger. Android now actually allows you to do MAC randomization, which prevents listeners from using MAC addresses to build a history of device activity. And so this is increasing your user privacy. All right. So basically, every time you go to Starbucks or whatever, your MAC address might change because they don't want you to know that how often you're there and those types of things. Because if they're tracking your MAC address, they can know how often you come into the store and everything else like that. And as we all know, data is a huge, huge business right now, is just collecting every little bit of information about you can. So that MAC address randomization is actually a nice little security thing if your device supports it. Not all devices will. If you're curious if your device does, I'd have to say go ahead and Google it. All right, I think it's a newer Android 10 type of thing. I have no clue about iPhones. But again, just kind of one of those things that you want to keep in the back of your head. So traditionally, not going to change. However, that's starting to kind of be a little bit different. Now, MAC addresses. We talked about how they're linked to the NIC tradition normally. So manufacturers are actually assigned MAC numbers that they can use. All right, so, or I don't know if they're assigned or they buy it, if you kind of understand what I'm saying there. All right, so they do have specific monitors or specific numbers that they can use. All right, so you can actually, do I have that? I do. What's my IP address, Mac? What's my IP address? Just do that. Of course not. That didn't take me where I wanted to. No, of course not. All right. But anyway, so you can look up devices based on the MAC address that you have in your computer. So really kind of an interesting thing. So you can be like, okay, what manufacturer produced this? Or if you do go onto your router and you're like, what the hell is this device on my network? You can find the MAC address for it because your router does have access to that. And then you can, from there, you're able to determine what device it is or what manufacturer it is, which gives you at least a better idea of what is on your network. So you're like, what is this? I don't recognize that. What device is there? And you can be like, oh, that's my Xbox. Okay, that's fine. Especially if you're doing a little bit of security looking up and those types of things. DNS checker. DNS checker MAC address. Now that's the one that I want. So if we go ahead and hit this button now, so here you can see, and we can type some things in. So just for fun here, let's type in the one that was on the screen: 10F00540F321. We go ahead and hit the search button there. You can tell that it is an Intel corporation. All right, they tell you their start address, their end addresses, the lot number. So this was lot number 8. Kind of interesting though how you can just look up that information. And here they tell you the address prefix. This is kind of like the 6 digits that they are assigned, and the next 6 are the ones that change depending on the device that you're on. So something definitely to kind of keep in the back of your mind. So this is going to be 6 sets of 2 hexadecimal digits. Now we did talk about hexadecimal digits the other day. All right. Remember those hexadecimal digits are there we go. 0 to 9. Man, I can't write. 0 to 9, and then A to F. All right. So that anywhere from that can occupy a single space, which means there are hexa means 16. All right, 16 different possibilities there, which means 2 spaces would be 2 to the 16th power. Which is a lot of different possibilities. 2 to the 16th. That's 65 possibilities in 2 spaces. All right, so yeah, that's right. So that's a huge number of different possible combinations of devices in just 2 spots. All right. As we go to more and more, obviously that number kind of goes through the roof. So that's just something to be aware of. So these are MAC addresses are used to identify machines within the same broadcast network. So this is going to be a layer 2 base of thing on the OSI model. Now, what your router does is it uses the MAC address. So when you plug something into it, it says, hey, what's your MAC address? And your computer sends your MAC address to it, and it goes, okay, I'm going to assign you this IP address based on your MAC address. Some routers are what I'm going to call smart enough or programmed to be that they always give the same IP address to the same MAC address. All right, which might not be a big issue for your Ethernet, something plugged into the router that's plugged in all the time, but for your phone, that's very convenient to have it always at the same IP address. A printer, those types of things, having those always be at that same IP address makes your life when you're trying to use a printer wirelessly a lot easier. But not all routers do that. I think a lot of them are moving to that, but just because they're moving there doesn't mean they're all there already. So So it's very convenient. Now you can go into your router and set a static IP address for a specific device that way. So you could say, anytime you get this MAC address, assign it this IP address. Or you could say on that device itself, you could say, anytime you connect to this network, this is the IP address that you're going to get, that you're going to request, basically. And by request, I mean, you're not actually even asking the router for it. You're just saying, oh, I'm on this network. This is my IP address. And I just set it. Now that could screw you in the long run, because that could, your router could have assigned that IP address to another device, which then causes conflicting information, which causes some problems. So that's not really a good thing. So when you're doing that, you do want to make sure that you're assigning it a static IP address at a location where it's not already going to be used. So we'll talk about that more in a minute. So there are, man, let's see. So this would be million, this would be billion, this would be, there's 281 trillion different possibilities. All right. So since this is 6 sets of 2, that would be 12 different options. So that would be 12 spots to the 16th power. Nope, that doesn't work. Oh, I'm sorry, 16 to the 12th. There we go. Yep, 16 to the 12th. That is how many different spots. You always put the number, whenever you're trying to figure out how big a number can be, the lower spot here is the combinations. So this would be combinations for that specific spot. And then when you go to a power, you guys can't see my screen again because I'm flip-flopping all over the place. There we go. And that power is the number of spots. All right, so in this case, we have 16 combinations and we have 12 different spots. So we do 16 to the second. All right. So yeah, that's what's going on there. And that tells you a super large number of different MAC addresses. I don't know if we're starting to run out or if they're starting to reclaim older devices. If they figure, well, these were all assigned to Intel and they gave them back out in 2000. No one's using a device from 2000 anymore, so they've started to reuse MAC addresses from back then. I don't actually know, but that is just something that you do want to be aware of. Now, while MAC addresses are used at layer 2 of the OSI, IP addresses, which we're going to talk about on the next slide, those are used at layer 3. All right, so those are used to identify machines throughout different networks. All right, and you may be going, why the hell do we have an IP address and a MAC address? We'll come back to that one. So your MAC address for your device, or not MAC address, your IP address. We're moving on. All right, here we have a lot going on. There are 2 different versions now of IP address, version 4 and version 6. All right. Version 4 is what I've gotten over here in that table, and also the bullet right below what I had circled. All right, so a version 4 address is 32 bits. All right, and we divide that into 4 different numbers. All right, so that would be 8 bits per number. All right, so that gives us a max possible combination, as we can see right here, of 255 for each of those different spots. All right, so that's what we're using there. Version 6 is 128 bits. So for version 4, we have 4.3 billion possible addresses. However, that is like total if you used every single one from 0.0.0.0.1 to 0.255.255.255.255. So all zeros to all 255s. However, as you can see from this chart, that doesn't exactly work out that way. All right. We have experimental and research category up at the top here, so not stuff that we're using on a daily basis for most places. We have multicast options, and then we have down here, we have specific ranges which are reserved for certain categories of things. And this is to keep miscommunications from happening once you're on the World Wide Web and those types of things. So you can see there is a bit of a gap from here to here, from A to B. All right, we only go up to 126, so we actually, in theory, we have from 127 to 128, 127,000, dot 000 to 255s. That's completely missing. We don't have a gap there. We don't have a gap there. So that's the only gap that we have that's actually missing. However, if you go on the internet, I think it was like 172 or something was what the IP address of Google was locally. 8.8.8, which would fall into this one, which falls into this category, is their DNS server. So, we're not using the entire version 4 bit for it to supply IP addresses globally. And the reason why we have version 4 and version 6 is actually because we're starting to run out of IP addresses of version 4. Like they are at, they're dwindling down, and we're starting to move on to version 6. All right. Version 6, I don't know if I actually said this yet, since it's 128 bits, that's 340 undecilan possible addresses. Undecilan. I've never heard of that prefix. All right. Just as a kind of comparator, that is 79 times 10 to the 25th power more add times more. So if you multiply the number of 44 version 4 to the version of v6, that is that many times more addresses. Holy crap, there. Find 25 zeros. I was going to write the number out when I first was looking this up. I'm like, oh, it'd be nice to be able to just write it on the screen. And I'm like, I'm not writing all those zeros out. That's a lot of freaking zeros. All right. So when it starts coming to the World Wide Web, www, we are slowly starting to transition to this version 6 thing. All right. A lot of home networks, you can use version 6. I believe my desktop that I'm using right now actually does have a version 6 address, although I've set it to be preferred to version 4. All right. And again, at home, this is never going to be an issue for home use, ever. All right. However, for the World Wide Web use, there is going to be a big problem there in the not too distant future, because as we keep adding more networks and companies and servers and things on the network, and more people have devices, it's starting to become a bigger problem. All right, so that is something that we do need to be aware of. Version 6, which I do have listed right here, as you can see, 1, 2, 3, 4, 5, 6, 7, 8 times 4. It's a lot of different bits. All right, so that is a little example of a version 6 IP address right there. So something along those lines. It is hexadecimal, which means we do have, remember, A through F and 0 through 9. So just something to be aware of. We have our private IP addresses, which are assigned by MAC, which I've already told you that. Now, let's go ahead and kind of dive in here. For our home small networks, most of the time, this is the network that you guys are going to be on. If you actually go into your computer, if you want to do it right now, and go ahead and pull up a command window, hit Windows button, and then do CMD, and then type in ipconfig. Once that command window opens, it will list out your IP address. And if you didn't know what it was, most likely it's going to be 192.168. something. Now this X does change. All right. Most of the time it is a 0 or a 1. All right. Not like because of anything binary, just that's the lowest one. So that's what most of the router companies set as their default IP address. You can change that. You can change just to basically be whatever you want. But yeah, so 0 or 1 is traditionally what X is. And then this Y part, that is what's going to change depending on your device. All right. Yeah, my next slide will talk more about that whole thing. So when we talk about routable, all right, and this goes back to the whole layer 3 thing for IP addresses on other domains. This is talking about how we get from one device to another, right? So we have you over here on the World Wide Web, that's your computer, and you have all these different routers connected all over the world. And we've talked about this to some extent. All right, and those are the backbone of the internet, and they're all maybe not connected directly together, but they all have different paths that they can take. All right, and then you're trying to get to some little server over here. And hopefully you've all heard of the game of 6 degrees of separation. Basically, within six people that you know, and 6 people that don't, so one person, and that person knows somebody else, and that person knows somebody else, and that person knows somebody else. In theory, within 6 steps, you can get to like basically anyone on the earth. All right, now it may be a rather large jump sometimes, but you might be like, yeah, I know that person. They're more of an acquaintance and a friend. Like I know their name, I've talked to them before, but I don't truly know who they are. But normally within 6 steps, we can get to like almost anybody. You're related there to somebody else. All right. So it'd be like change color because we can purple. You can go from here to there to there to there, and that gets you to that endpoint. But if some link goes out or whatever, you can take a different path. All right, so a certain backbone or whatever is down. All right, now the main reason that I have found, at least, that we have both MAC addresses and IP addresses, all right, is it keeps a network cohesive. Since MAC addresses are assigned by the vendor, all right, they're all over the place. One device on your network may be of Intel, the next one may be Microsoft, another one would be Sony. The list kind of goes on and on. So those those MAC addresses are going to be all over the place when it comes to their numbers, which makes jumping from one device a bit harder, because you're like, well, where's that located? Is it local? Is it a faraway thing? So it's hard to kind of group things together. IP addresses, on the other hand, when we assign them, again, your router is going to be your IP of your router is going to be probably like 192.168.0.1 or something like that. This one almost guaranteed. This 0, that's a question mark. That one, I said, that one may vary. And even these first two can vary slightly. But most traditionally, it's going to be that. All right, I think every router that I've ever bought, it has been this. Now, if you're on Comcast, on the other hand, and you have Comcast modem in your house, you're actually going to fall into this Class A group. I don't know why Comcast does it, but their routers sit at 10.0.0.1. That's kind of hard to see. Maybe we're going to go back to our red color. Anyway, 10.0.0.1. All right, that's probably where your Comcast router is if you're renting it from Comcast themselves. But this kind of groups us. So some routers, again, will also do these numbers consecutively. So the first device that connects to the Wi-Fi the network will be 100. The next device will be 101, then 102, then 103, etc., down the line. Some devices do this somewhat randomly. So they start at say 100, but they go to 254. And they just kind of pick a number in between there. So your first device may be 113, your second device would be 152, your third device would be 208, fourth device should be 102. The numbers kind of become a little bit random, per se. And I don't know if those are based on your MAC address, which is why they're that random, or what the case is there. I just realized that I was writing behind my picture again. I really need to put like a box here so I don't write in that corner. But anyway, hopefully you kind of get that idea. But by assigning IP addresses to MAC addresses, everything becomes cohesive. We know what's on my network. We know what's not on my network, what's out in the World Wide Web, those types of things. All right. So that's the best answer that I have why we have MAC and IP addresses. There's another example coming in a minute. So here we have IP address, and this is going to be such a huge part of anything industrial that you guys are working on, is subnetting. All right. So here we have a nice traditional little IP address. And again, this is going to be your house. All right. So the network, what we have, and there's two ways of showing the subnet information. Way number one is this /24 here. Way number two, which I find to be the more common one, is this 255.255.255.0. All right. Not necessarily it's going to always be this subnet. That is the subnet right there. But that's the more common way that I have seen for it. And if we would break this 255 down into binary, that would be a 1, 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot. I'm gonna run out of space. 1, 2, 3, 4, 5, 6, 7, 8 dot 0, 0, 0, 3, 4, 5, 6, 7, 8. All right. So if we break that number down to binary, that's what it would come out to be. And if we would count the ones, you probably, hopefully, have guessed this already. There are 24 ones there. All right, 3 sets of 8. All right. Now, what this subnet mask does, if we put it right below our other network here. Yeah, just go ahead and write that in. 4, 5, 6, 7, 8. All right? That tells us what is the network portion of it versus what is the device. All right, so our network portion versus our device. So anywhere we have a 1, that becomes the network portion. So that in this case stops right here. All right, anywhere we have zeros, that would be our device portion. So this is a nice overall simple way to actually kind of separate things out. And if I remember correctly, I did already do this. Let me just double check this. So 120, yeah, 126. Yep. So this is the binary. Sorry, I'm actually drawing a thing. That's the binary for that IP address. All right, that's what's going on here. So this is telling us that the network, and the way I like to look at network is it is like a street address. It's the street that you live on. All right. So I live on street, 192.168.52, and the address on that street is 126. That is how I look at our network portion versus our device portion. I find that to be the best way to explain things to you guys. Simple. I could go through how to convert things from binary to decimal. And some of you who have taken my PLC class, we've already talked about this. 2, 3, 4, 5, 6, 7, 8. And it's actually in the long run very simple to do. At least binary to decimal is very easy. Going the opposite way, decimal to binary, is a bit more challenging. Oh, I skipped 64. I'm like, something doesn't add up. Sorry, let me go back. 64, 128. So if I want to put a binary number in here, let's just go with 001000010. All right. All you would do, I wrote the binary digit equivalencies on the bottom, is you just multiply. So 0 times 1 is 0. 1 times 2 is 2. 0, 0, 0, 32, 0, 0. And then you add those up, and that would equal 34. So 34, the binary equivalent is 001000010. All right. If you want to go the opposite way, all right, go ahead and just erase all of this and erase that. All right. Let us kind of pick a random-ish number. Let's go with let's go with 57. That sounds like a good random number to me. All right. So what I like to do, and if I'm going this way, I'm doing it by the long way. I'm not just cheating using a calculator. What I do is I say, does 128 go into 57? No, it does not. It's too big. So that gets a 0. Does 64 go into it? No, that gets a 0. Does 32? Yes. So then I would just do a little, simple math here. That gets me down to 25. Does 16 go into that? Yes. Minus 16 again. That gets me a 9. Does 8? Yes. That gets me 1. Does 4? No. Does 2? No. Does 1? Yes. All right. So overall, it's really not that bad of a process to go either direction. But it's definitely, to me, simpler to go from binary to decimal than decimal to binary. It's just a simple math. And, I mean, going the opposite way is too. Now, if you're kind of like me and you're feeling on the lazy side, Windows does have a calculator built into it. Now, normally when you open your calculator up in Windows, you get this standard calculator right here. All right. However, if you go ahead and click on the 3 little lines at the top, the programmer option is your best friend, and allows you to click on which type of number you're entering. So in this case, I'm going to say I'm going to enter a decimal. I'm going to type out 57, and then here you can see 001110001, and that would be what we came up with. All right. Now, if you want to say, okay, let me enter. This would say 57 in decimal is 39 in hex, or 71 in oct. All right. So it allows you to go like all over the way. Bit toggling keyboard. Oh, that's just cruel. Okay. Anyway, we're not going there. If you do click on the hex, notice that you now actually do have the option for letters. So let me just go ahead and say F. So F is the equivalent of 15 in decimal, or 1111 in binary. All right. So it's kind of nice that you can just pop this up. Real easy, super simple to do. So just kind of something to think about when you are working with these types of things. So that Windows 10 calculator is actually pretty darn nice in the long run for doing conversions and things like that. So subnetting. Now, down here at the bottom, let's go ahead and clear all of my text again. I have another one. And this one is much, much, much more complicated, all right? So I have the same address, 192.168.52.126, but my subnet has changed now to 21, which is a equivalent of 48, all right? So remember, 816, so that leaves me 5. So if I were to write the subnet out again, it would be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's 16, 17, 18, 19, 21, 2, 23, 24, 2, 3, 4, 5, 6, 7, 8. All right, so now we have less ones, which means we have our dividing line, where up here we were divided right there. We're now going to divide it here, which is actually in the middle of this third number, which is where this gets really interesting. This .52 actually probably wouldn't work in this situation. Yeah, I probably screwed that one up. But anyway, let's just continue like I didn't screw that up. Because that would probably have to be bigger than 248 in the long run. So it would have to be like, 248. 248 would be one, or 249, 250, 250, whatever, above that. But it would have to be above this this number right here. So if we again would rate this all out, we would now have more digits. So instead of having 8, which is a possible of 256 different addresses, we've now added 9, 10, 11. Right? So remember, that'd be 2 combinations to the 11th power. All right? We've just skyrocketed our possible combinations here. So 2 to the 11th equals, we now, instead of have 256, go back. So at 256, we now have 2,048 different devices that we could put on the network. All right. So subnetting becomes really important when it comes down to dealing with network devices and things like that. The good news is, unless you guys are going into the IT field, you're probably not going to ever be dialing that far deep into this. Most likely, you're going to talk to your IT department. You're like, we're adding a network device. I need an IP address for it, or what's the information for? What subnet? What's the network? Those types of things, and then you'll pick it, and go from there. So you're probably not going to be the one deciding these types of things, but they are very important. All right. And I should have said this from the get-go. The quickest way to explain subnetting is it's the process of taking a network and splitting it into smaller networks. All right. So a lot of give and take is going to be going on here in the long run, but definitely something to consider about. And again, at home, using this traditional subnet of 24, plenty of devices. All right. I don't know how many of you guys have how many devices on your network. Go ahead, take a quick second and count how many devices are on your network. All right. Think it through, go through each room, and if you want, just go ahead and type it in the chat just so we all know roughly how many devices you have connected to your home network. I'll give you guys a few minutes to do that. All right. Heidi says they have at least 50, and it would take her all day to count them all. All right.
We have Unisoft. I don't know if you have heard of it. So it has really cool software that it actually like draws you a whole map of everything that's in it.
Mm-hmm.
So I don't have the software on my computer on this one. Otherwise, I could have just went into the software and counted everything.
Yep.
But it's like super complex in my opinion.
Yep. No, I mean, the Unisoft is more than I'd say it's like a level above traditional home grade networking equipment. So it's got to be a bit better.
Yeah, and clearly I'm not the one running it, so I'm sure you picked on that.
All right, Austin, how many do you think you have in your house? All right, Cheyenne said they've got about 20, give or take a few. Austin, Jacob, what do you guys count? I like how the girls are the ones that are willing to talk and send messages. All right, I looked actually at mine. Oh, Austin says around 20. All right, I actually pulled up my router at my house, and according to this, we now have 26. A minute ago, it was only 25, so I don't know what just got added to our network. But with my router, I can click on this, and it shows me a list of all of my different connected clients with all their IP addresses and things like that. So yeah, we've got a few Wii's going on in the house, the old Wii's. We got cell phones, laptops, those types of things. So there's a lot going on in our house. I also do home automation things, so I can turn things on and off remotely, which I always find amusing. So I've got 26 with my home automation stuff, which I thought was going to be like the winner here, but you guys are a lot closer than I was expecting in the long run. So that's interesting. But anyway, so again, you're all not even close to that wonderful 255 max number. All right, network. Yeah, this does. Oh, let me hit the advanced button. There we go. Let me go back to my zoomed in here. So here I have my little zoomed in section on my router, and you can see that my IP range for this, when it's assigning things, it starts at 100 and only goes to 199. So I'm actually only capable of assigning via DHCP, which is Dynamic Host Communication Protocol, I believe. I only have a capability of assigning 100 different devices to my network automatically. Now you can change this. Again, you could start basically as low as 1 or so and go up to 254. No, you can't go to 1. You have to start at like 2 because the router is 1. And 255, I believe, is a broadcast, so 254 would be the highest you could go. But still, you're probably way above anything that you would actually need. But like this gives me space to manually assign things below this 100 mark. So if I wanted to just set my server default to something on the server itself, that's where I could do it, is on the server and go. As long as I'm below 100, we're good. So just something nice to be able to look into and kind of have a better idea of what's going on with your information. So, all right. Now, here we have, let's go to the next slide. There we go. Here we have a little animation of you sending information from one computer to another computer over the internet. And as you can see, the MAC address keeps changing as it goes from one hop to the next. All right. So basically, the data doesn't change, and the blue would be the destination IP address. So that would be the IP address of, and why is it going to do that to me? That would be the IP address of this item down here. And if we would, think of that in the world of Google, let's say 8.8.8.8. All right, that would be what that blue IP address is. So it goes from, your computer, which says, hey, this is my the MAC address, and your computer basically says, hey, I'm trying to get here, and it goes, oh, the MAC address of this router is, A. So right off the bat here, when it assigns a MAC address, it says, hey, go to A, and then this one would be B. So this one changes the MAC address and says, this is your destination, and it tries to get there. And then that changes it to C, and then C changes it to D. All right, and that IP address at the top doesn't ever change. All right. And that's because that's what it's saying. This is where I'm trying to get to. So every time it goes from one hop to the next hop knows, oh, we're still trying to get here. So that way it knows how to focus your attention or focus that packet. So that IP address doesn't change. There's another piece of this, which I think I do have in another slide. Let me quick check that. Yeah, we talked about headers, so we'll come back to that in a minute. All right, next we have DNS. All right, DNS is a dynamic naming system. I like to think of this as a glorified phone book. All right, this maps URLs to IP addresses. So when you go in your web browser and you say go to google.com, this does that to me. Go to google.com. All right. What your router does is it says, I don't know what google.com is. So it sends a message to the DNS provider and says, hey, what the hell is google.com? All right. And then that sends back, oh, Google is, 172. Blah, 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 blah. All right. And then your router goes, oh, okay. And then it sends its packet of information out to, Google. All right. So this is a beautiful naming system. There are multiple different DNSs out there, and there are multiple different DNS servers from each of those different DNS providers. I have a few of them listed here. So Google is 8.8.8.8 if you want to use Google's DNS, and their alternative or their backup one is 8.8.4.4. Another one is 1.1.1. That would be, that's actually, I think, the name of the website or company. It's 1.1.1.1. You do have, so here you can see, and 1.1 is trying to claim that they are the fastest, they're going to increase your internet speeds, all right? And here they could show you their latency or their ping times or whatever they're showing you. So they're saying if you use us, it's going to be a 13.66 milliseconds probably before you get your response. If you use Google, it's going to be 23 milliseconds almost, all right? So you want to use us because we are 10 milliseconds quicker, all right? Now, will you ever notice the difference of 10 milliseconds? Probably not. All right, that is not something that's probably going to be an issue for you, but that is something to think about. So they are trying to say they're the fast and reliable. So yeah, to each their own. You're welcome to use them. You can use your own. You can specify this. If you do not specify one, your ISP will specify one for you. So if you don't have one specified somewhere, and there are multiple different locations that you can specify a DNS. All right, you can specify it on individual devices. So you could say, hey, I want to use this DNS server. You could also specify it on your router. So actually, does look like my advanced settings up here. Of course, oh, probably have to go to static. I don't know. Anyway, if I come back to my network connection here, you can see that my primary DNS server is 192.168.0.111, and you may be going, that's a private IP address. What the hell's going on there? Well, I have something installed at home called Pi-hole, which isn't working completely properly anymore. But basically, what Pi-hole does is it's an intermediary DNS blocker. All right, it's kind of like a glorified ad blocker. So Pi-hole basically is running on a computer in my house, and it basically any request for the internet, it goes to that first, and that says, hey, yeah, I'm looking for this address, and it goes through and it says, okay, you're looking for ads.com, and my Pi-hole goes, those are ads. We're not going to show those to you. And it just basically blocks that request. It never sends that out to the DNS. So whenever I go to websites, I get a lot of like empty boxes or X's and things that where ads should be. If it is not on its magical blacklist of these are bad websites, it then sends that request actually out to another DNS provider and says, hey, what's the address for this? So I actually am adding latency to my DNS request, but it's helping me block ads. The fact that my secondary one here is 8.8.8 is actually causing problems for me, I think. So I need to go through and actually go and modify that at some point, because that shouldn't be there, because that's basically allowing some of those ads to get bypassed. So I need to go look into that one. So you can specify your DNS, as I said, at the computer level or at the device level. You can specify it at your router level, those types of things. So to each their own is really what it all comes down to when it comes to DNS. Now, let's truly get into the whole reason for the shindig. Well, I mean, we've already hit up a good reason of this. But TCP. All right, so TCP is Transmission Control Protocol, and it's in this case for /IP, which is Internet Protocol. All right, um, so that is what TCP IP is. Um, it is the de facto global standard for the internet, basically network and host-to-host transport layer implementation of internetwork applications because of the popularity of the internet is what it comes down to. So basically, when you are using your computer trying to access the internet, you are using TCP IP. There's no other way around it. All right, so over here on the left, we have the OSI model. All right. I also have the Arpanet model used right next to this. All right, so remember we talked about Arpanet was basically the precursor to the internet and all those things. OSI was actually developed in Europe by the International Organization for Standards, which is ISO. Hopefully you've heard of ISO before. So this was in Europe. This is obviously kind of the old school US one, and they kind of show how things line up. So the internet layer is equal to the network layer at layer 3. The transport is equal to 4. The ARPA model has only a layer 1 and 2 combined, and the application layer for ARPA has 5, 6, and 7 combined. So, but here you can see where the TCP and the IP are. So TCP is at level 4. All right. IP is at level 3. Right, I need to read my notes. All right, now IP, let's start with TCP. So TCP is service or host-to-host. So we're talking about the layer here. All right, the transport layer, so layer 4. This is using 2 different protocols that you might have heard of. All right, one of those is, and let's scroll back down. UDP, which is User Data Protocol. This is a connectionless or unreliable protocol used for higher layer port addressing with minimal protocol overhead. All right, which means it's going to be a little bit faster, but it's also unreliable or connectionless. So TCP, on the other hand, is a connection-oriented protocol that's a very reliable method of transferring a stream of data in byte format. So UDP basically says, "Hey, I need this information," and not like, "Hey, I have a question for you." It's kind of like raising your hand in class, right? That's more of a TCP. You raise your hand, I get a connection with you. I go, "Cheyenne, what's your question?" And you answer, or you ask me your question, then I respond. We go back and forth a little bit, and then our communication is over. UDP is just you blurting out a question and me having to go like, "What did you just say?" All right, because I only could focus on one thing at once. Computers are overall very good at can be focusing on multiple things at once, so it's not as big of an issue in the long run there. So that's the difference between UDP and TCP. So you might have heard about that. The TCP is responsible for data integrity. So that's one thing to look at. Now, IP on the other one is the internet layer, all right, or network. So layer 3, all right. And this is the primary responsibility is routing packets from one host to another. So remember, if we would go back those 2 slides, if we go back to this one, this is routing the information, all right, from one location to another. All right, so that is what we're talking about here. So the IP is the dominant protocol here. We do have address resolution protocol, which is ARP. We have reverse address resolution protocol, which is RARP, and we have the internet control message protocol, which is ICMP. ARP is used for the translation of IP address to a hardware MAC address as required by Ethernet. ARP does the same thing. It complements ARP. And then ICMP is a protocol used for exchanging control or error messages between router or hosts. So again, just kind of another thing to keep in the back of your mind. Now, here we have a network frame. All right. So the header, the local network header and the local network trailer can change depending on the network type that you are on. So it may not always be a network, it could be something else. And there are different types of networks out there that your data gets passed to without you ever knowing it. All right. There are ways that you can kind of control that, which we'll talk about in the IP packets, but we'll come back to that one in a minute. So that information could change. The IP datagram, so from here, it even showed me a little dot. From there to there, all right, is not going to change unless you move to a network that has smaller packet sizes. So let's just say this is a 16-bit message, right? From between those two lines. And we're transferring on the Ethernet, which is perfectly fine. But we go to some network type that is only an 8-bit message size. Well, all of a sudden our 16 isn't big enough. So now we're going to take this and we're going to split it up into 2 messages so we can get transferred over that network type. And at that point, we'll then combine it back once we get back to an Ethernet or something. So we will reassemble that. But otherwise, when we're getting passed from one router to another, nothing in this datagram, this IP datagram here, is going to actually change. It is going to stay consistent, I said, unless it's on a network with a smaller packet size. So here we have our IP, all right, and this is going to be responsible for delivery of packets. And this is the IP header, purely the header, all right. This is a minimum of, I believe it's 5 32-bit words. So here they're showing you 32 bits side to side. So we have 1, 2, 3, 4, 5, minimum of that. And this last one here, this is an optional one, all right. So a lot could go on here. In this header, we have a lot of information. So we have version. So this is the version IP we're being used. So that'd be right here. We have IHL, which is the internet header length. And this is important since the header length can change. So that would be, how many of these different bits are we going to be using? We have our type of service. This informs a network of quality. Do you want to go have your information transported as fast as physically possible, which may, you may not have to wait to get your data transported, but it may actually go through a slower network. You need your max throughput. We're streaming video. We need to be able to handle 5 megabits per second constantly. Do you want max reliability? Do you want the one that's going to have the least errors issues because of, maybe age of fiber optic cables or something? Or do you want the one that's going to be the least cost effective? So that would be our types of service. Our total length, I think, is pretty self-explanatory. Our identify is uniquely identifies each datagram sent by a host. So this is kind of like a tracking number in the Postal Service. Basically it's that it's actually the number itself. It's not the tracking purpose. It's just that number. Then we have our fragment offsets, which are used in case of fragmentation, and it's used to reassemble things. We have time to live, or TTL. This ensures that undelivered datagrams are eventually discarded to make sure that we're not just waiting constantly forever for something to show up that's not going to because of some error. We have the protocol, so we have ICMP, TCP, UDP, and then we have our checksum, and this is for our error checking. And then again, notice we have our source address and our destination address. All right. So again, these probably would be our MAC addresses, or no, these are actually probably our IP addresses. So this is our final destination. Now, I should say, when you send an information request out from your computer at home, because you're on a private network and the internet does not work on private networks, it actually uses your router's IP. All right. And that is using and it does that via NAT or PAT, all right, which is network address translation or port address translation. So basically what it does with PAT's the easier one to explain, is when your computer, right, we have our home router here with all our different devices on it. When your computer says a request for Google, it comes through and basically your router goes, okay, we're going to assign port 36 to that request. So it has its IP address of whatever it is. So we have our IP here. And it's :36. And then it sends that all the way out to Google. And then when the Google request comes back, it comes back in on that same port, and the router goes, oh, that was sent on port 36. I forward that to this person over here. All right. So that is how PAT basically works. And that allows you to have a whole bunch of different devices sharing one external IP address. All right. So kind of a nice little capability there. So our IP is, the whole point of this is to forward and deliver datagrams of the basis of IP addresses attached to the datagrams. This is in the same way that postal service would process a letter based on the postal address. So again, just kind of passing that information from hop to hop to hop to hop to hop. All right. This has been a lot of networking jargon and information, and some of this stuff will probably be something that you never actually use. All right. However, This type of thing also allows you to talk to networking people very nicely. And when you can have a conversation with IT people and actually they understand what you're saying and you understand what they're saying, they become a lot friendlier. All right. This is something that I've learned over my time teaching and that man, having IT people on your side is a wonderful thing, and keeping them happy is even more wonderful. So being able to understand and have a conversation with them is just so useful in so many different ways. So um, this is probably a bit more than you're going to ever talk to your IT people with, but if you can say, yeah, I need some more RAM or things like that in my computer, which we didn't talk about in this lecture, but um, still, being able to talk to your IT people will make a huge difference in how they react with you and those types of things. So really a nice capability to have. All right, and that is basically all I've got on TCP and IP.